Now we will see the diagonal relationship. The similarity in properties existing between the diagonally placed elements is called diagonal relationship. On moving diagonally across the periodic table, the second and the third period elements show certain similarities, even though the similarity is not same as we see in a group. It is quite pronounced in the following pair of elements. See, lithium is different. It is not only showing the properties of its own member, it is also showing some properties similar to the diagonal member. Magnesium. Lithium is the first member of the first group. Magnesium is the second member of the second group. They are similar. They are, see, that much similarity is not there, but to some extent similarity is there. Okay, but it is there, no? That's why we have to study this diagonal relationship. In the same way, beryllium diagonally related to the aluminium, boron related to the silicon. So this what diagonal relationship is there with other members also, but it is less. But here with these three pairs, lithium, magnesium, beryllium, aluminium, boron, silicon, these three pairs are the best examples for the diagonal relationship. Okay. See, the data says, if you see the lithium's ionic radius, lithium after losing one electron, 1 plus, okay, and if you see the magnesium's ionic radius, second member of the second group, right? Magnesium after losing 2 electrons becomes Mg2 plus. This is after losing 1 electron becomes Li1 plus. So Li1 plus and Mg2 plus, if you see their size in picometers, almost same, 72, 70, very close. I'm not saying similar, almost same. Because of similar ionic radius, they are somewhat similar in the properties. It is the size of their ions and size of their atoms which is very close. They show somewhat similar properties, and this is known as diagonal relationship, proved data wise, property wise. Now we'll go to the chemical reactivity. Okay, periodic trends and chemical reactivity. The physical and the chemical properties of elements depend on the valence shell electronic configuration as discussed earlier. The elements on the left side of the periodic table have less ionization energy and readily lose their valence electron. That is the left side. Already we know in the IE trend. On the other hand, the elements on the right hand side have electron affinity or electron gain enthalpy and readily accept electron. That means extreme left ready to lose, extreme right ready to gain. As a consequence of this, elements of these extreme ends show high reactivity when compared to the elements present in the middle. If you see the modern periodic table, the most reactivity you will find either in extreme left or extreme right, not in the middle. Extreme left ready to lose electron, extreme right ready to gain electron. So this is there only with the extreme end, but in the middle moderate reactivity is there. That's why in the 10th class you have seen the reactivity series of the metals. The most reactive metal was potassium as per the 10th class. Potassium belongs to what? Extreme left side. And if you move in the series, copper, nickel, they will come. They are the members of the middle block. Okay. So left and right are the most reactive elements on the modern periodic table. About the noble gas, already you know very well, they are chemically least reactive. The IE is directly related to the metallic character, and the elements located in the lower left portion of the PT have less IE and therefore show metallic character. That means left hand side elements wants to lose electron readily. According to the electronic definition, the one which loses electron easily is the best metal, and the best metal you will find where? On the left side, that too left below. On the other hand, the elements located in the top right portion have very high IE and are non-metallic. That means On the right side, they don't want to lose electron. So they want to accept electron. So they behave like a non-metal. So the one which is readily giving electron, metallic. The one who accepts electron, non-metallic. And best non-metallic we will find, best non-metallic will find right top. Let us analyze the nature of the compounds formed by elements from both sides of the periodic table. That means we will analyze by taking some example, left and right combination. Consider the reaction of alkali metals and halogens with oxygen to give corresponding oxides. So here I have taken example of what? One example for alkali metal with oxygen and example for one halogen with oxygen. Alkali metal with oxygen, sodium with oxygen gives sodium oxide. Now extreme right, chlorine, halogen, okay, with oxygen gives its oxide, chlorine oxide. Now what is the nature? Since sodium oxide reacts with water to give strong base called sodium hydroxide, it is basic oxide. Sodium oxide, when you put in the water, it dissolves and converts into what? Base. Therefore, this oxide is called what? Basic oxide. Why? Because this forms base in water. Whereas, what about this oxide? This oxide in water, it gives acid. Which acid? Perchloric acid. Therefore, this is called acidic oxide. Extreme left side oxide, because they give base, are called basic oxide. Extreme right side oxide, because they give acid, they are called as acidic oxides. See, sodium oxide in water giving sodium hydroxide, so it is called as basic oxide. Whereas chlorine oxide in water giving the perchloric acid, because this oxide forms acid in water, therefore this is acidic oxide. Thus the elements from the two extreme ends, left and right, of the periodic table behave differently. As we move down the group, the IE decreases and the electropositive character of elements increases. That means when you move from top to bottom, IE decreases. Giving electron is increases. Metallic character increases. Electropositivity increases. Hence, the hydroxides of these elements become more basic. For example, let us consider the nature of the second group hydroxides. Second group, beryllium is the first member. Okay, then followed by magnesium, calcium, strontium, barium, radium. So let us see their hydroxides. All forms hydroxides. Okay, but what is the nature? Beryllium hydroxide is amphoteric, which reacts with both acid and the base, whereas next member hydroxide is weak base. Only with acid it will react, whereas the bottom member is highly strong basic. Okay, that means though they are the hydroxides of the same family, but behavior is different due to the small size of beryllium, especially beryllium. Beryllium hydroxide reacts with both acid and the base as it is amphoteric in nature. I told. Let us see how it reacts. See, beryllium hydroxide with HCl giving beryllium chloride and water. Okay, it is reacting to acid. I told as well as to the base. Now we will see the with base. Beryllium hydroxide with sodium hydroxide gives sodium berylate or sodium beryllium oxide. That means beryllium hydroxide is the first member hydroxide, which is different, amphoteric in nature, reacting to both acid and the base. Okay, boys, till now we understood the chemical behavior of the periodic table. This is a small idea. Still, we learn a lot in higher classes. Anyway, let us conclude today's discussion. And you are all going for the monthly test. So, I wish of the third chapter periodic table. But this is the not end. This is the end for the beginning. That's why I have shown this picture, sunrise. Let us begin well the next chapter. Okay. So this is a beautiful photograph of sunrise. It is a special photo taken from the spacecraft 400 kilometers away from the Earth surface. From the space shuttle it is taken. So beautiful it was looking. I want to share with you all. So sunrise is always something rising, something developing, something burning. Okay, something new, some new ideas are coming out. So we will start the next chapter with more and more ideas. So we have to born what someone said, no, we have to reborn every morning. So with this caption, I wind up my today's session, and I also welcome for the next chapter. And once again, all the very best. Thank you, my dear students.